Let us look at the law of gravitation. The gravitational law simply states that the force of gravity will be equal to G, which is a constant, times two masses that are attracting each other over the separation between them. This is a inverse square law where G is equal to 6.67 times 10 to the power minus 11 newtons square meters per square kilogram. Now, if we assume that one of the masses is the mass of Earth, and we take r as the radius of Earth, then we can simply see that F will be equal to some constant multiplied by the mass that is attracted to the Earth. That constant is called G, which is the gravitational acceleration, and is given by the big G multiplied by the mass of the Earth divided by the square of the radius of the Earth. Now, G is 9.81 at sea level. Sometimes we get more than two bodies that are attracting each other using this inverse square law. And how do you treat that situation? Let's imagine a system of masses that are scattered around like that. And we imagine that that mass in the center is pulled by those surrounding masses. The net force will be equal to the summation of the forces that are exerted by the surrounding masses. You can also have a situation where you can't separate the individual forces. And in this case, you need to use the integral instead of the summation, as the summation will be sufficient for discrete forces and the integral will be more applicable to continuous forces. Here's a question just to tickle your fancies. What is the difference between the free fall acceleration and G, which is the gravitational acceleration? Think about this. Don't just jump to the answer without applying your mind. Secondly, what is the difference between the measured weight of an object and its force of gravity? To answer this, I want you to think of the following hints. Number one, the Earth is not purely spherical. How does that affect the gravitational acceleration as well as the weight of an object? Secondly, the Earth does not have a uniform mass distribution throughout. In other words, the density of the stuff that makes up Earth is not the same throughout. To understand this better, let us imagine a graph of density against the radius of Earth. Closer to the center, or in the inner core, you've got higher density compared to at the surface. And that's why we're saying the Earth does not have a uniform mass distribution. But in most cases, we assume a constant density just to come up with a simpler model for mathematics. Now, assuming that the Earth is a sphere and it has a constant density, we can write the law of gravitation as follows. But if we want to make it as a function of r cubed, we also then have to multiply with r so that it can cancel out. Now this stuff is constant, especially if the density is assumed to be constant. We can take this constant and we make it k, small k, and immediately we realize that this equation is similar to what we refer to as Hooke's law. And Hooke's law is a law that normally applies to oscillatory objects. Now, what does it imply here? It implies that objects that are dropped through the Earth would oscillate. Think about that. Now, I want us to also think of the Kepler's laws of planetary motions. There are three laws in this regard, and the first one is called the law of orbits. What it says is that planets revolve around the sun in an elliptical path, and the sun will be at either of those 2 points called the focal points of the ellipse. And this is the first law of planetary motion. The second law is known as the law of periods. The law of periods simply states that when planets move around the sun in that elliptical path, they sweep equal areas at equal times. Now, this area A1 will be equal to this area A2 for any given time period. The line connecting the sun and the planet sweeps equal areas at equal time intervals. And what this means is that planets would move faster closer to the sun compared to when they are far away from the sun, where they are expected to go slowly. The last law is called the law of periods. This law, again, we place the sun at the focal point and we define two terms, one of which is called the eccentricity, which is the deviation of the ellipse from the spherical shape, and then the A there will be the semi-major axis. The square of the period will be directly proportional to the cube root of A, and it can also mathematically be expressed in terms of R as follows. Right, let's look at what we've learned so far. We've looked at the law of gravitation, and we've said that we can actually define a superposition of forces. We can use a summation for masses that are discrete, and we can define the gravitational acceleration as shown. We can also find the potential energy as described by simply dividing the force by the radius. We spoke about the escape speed, and finally we spoke about the Kepler's laws. And let's meet during tutorials where we'll be looking at various examples and exercises relating to these topics. Till we meet.